Hello guys, welcome to this episode where we will walk through onboarding a large language model onto the OpenAGI the AI Grid platform. So we are in this stage. The tutorial is on the second tutorial, part 1. And we'll be using this model onboarding Python notebook to do this tutorial. Today, actually, we'll focus on the real power of OpenAGI ecosystem, where we are treating the models like digital assets, orchestrating their life cycle, and enabling scalable production-grade AI, all without worrying about model conversion or quantization as well, right? So, uh, so the OpenAGI AI Grid is a decentralized modular platform for AI development and deployment. So the model for this tutorial is the famous Gemma 3 27 billion parameters model from Google. So before we dive in, let's see where we are in the AIOS ecosystem once. So I have this AIOS ecosystem architecture diagram. So this is the overall diagram, but where we are is currently here. So you can see, right, we are in the stage of onboarding a block as a digital asset to the AIOS ecosystem. And later we will be covering things related to metrics, autoscaler, load balancer, router and ad hoc inferencing servers as well, right? So, so we will touch upon some of the components of the AIOS ecosystem, like the assets DB registry. So we will touch upon some of the components of the AIOS ecosystem, like the asset DB registry, which is a central log for discovering and managing versioned runnable software components. Like basically, it's a registry of all the models and any other policies, any other logics, different versions. Even in the same Gemma model, we can have multiple versions with different quantizations. So it is a registry for that. And then we have a resource allocator, which is responsible for scheduling and allocating resources for these assets when we are doing when we are running it in the cluster. And we also have cluster controller, which manages the life cycle of the block, which is the it also understands what is the load of the model at any point of time, things like that. And it takes care of where we have to allocate the block, and it takes care of the necessary permission and other things as well. And we also have the metric system, which is a comprehensive system for monitoring the health status, like the CPU utilization and other things, right? So in this guide, even though the AIOS ecosystem is vast, we will touch upon some of these topics, like in the request that we do to register and all. We can see that as well, right? So the overall onboarding process, I have a high level description here, like what we are going to do in this tutorial. So the first thing is we will create a component.json file which describes our model. Like it is like the passport, right? So with some metadata, the versions and parameters that our models have, right? So first we'll be registering an asset into the AIOS component registry. Then we will see how to allocate a block, and then we will check the live metrics, its health status as well. Then we will do one inference also to understand with the gRPC we'll do an inference to understand whether we are getting the response from the allocated block or not. Then later we will also have a small tutorial on using the advanced streaming facility of the model. We'll show with the Streamlit UI how we are streaming, and we can send a query via the Streamlit UI, and we can see how the model streams and responses as well. And towards the end, we will see how to clean up, like if we want to deallocate or deregister the model that we have already registered in the AIOS component registry, we can do that as well. And the deallocation is to remove the allocated model in case we don't want to do any serving. We don't want the model to be up for some more time, right? So this is the high-level diagram. I will come to that in like once we get a grip on what we are doing here. So one note on using the pre-built Docker images. So we can actually, what we have done is for the easiness of to get started easily, we have done, what we have done is we have pre-built some of the images. The Llama 4 Scout also we have pre-built. The Gemma 3 model that we are going to do now, right? That also we have pre-built. We have a DeepSeek version as well. We have a Mistral version as well, and we have Quen version as well. So what I'll do is to for the sake of the tutorial, I will be using this Gemma 327 billion Docker image, and I will show you how to register it in the registry and so on. But in case if you guys want to use a custom model, like if you want to use a different model from the Hugging Face or something, and you want to see how you have to and you want to onboard it into the AIOS platform, for that we have a separate tutorial for which you can refer to this custom model onboarding, right? So registering an asset. So let's see what's there in this section. So first we need to define our model as an asset, right? So what is an asset? An asset is a static, a versioned, a kind of a specification for the model that we are going to onboard, right? So that and where we are onboarding it in the AIOS asset DB registry. So it acts as a central catalog, so that developers can discover later in some of the steps like routing, ad hoc inferencing, and all. We can also have a discovery stage to select the best model that we want, right? So that we can reuse it across the AIOS ecosystem as well. So by registering an asset, we are actually making it available for the deployment on the AIOS network. And for deeper dive, you can check this link as well, where there are more informations related to how the registry is organized and what are the APIs and services for registering this, and what is the schema used. You can get an idea here as well. So let's see, let me run this line where I already have prepared a component.json, which is the component.json for the Gemma model. Let me run and show you what is there in it. So actually we have several fields and parameters, right? But some of the important things I'll just mention here. So the most important thing here is the component ID, right? The unique name. So here I am declaring it as Gemma 327B and the version 1.0.0 and the release tag, right? So if you have a different release tag like production and all. So that is the component ID for you, and the component type. So here we are registering, since it's a Gemma LLM model, I'm registering it as a model. Probably if you have some other types, we can register that as well and later use it for spinning up as a separate service. And here we also have this container registry info, which points to this container image that I was the Docker image I was telling you about, right? We have some pre-built Docker images, Gemma 327B in this registry, and that's what I'm pointing it to. So that is the information. We can also have other metadata like author description as well, like this, right? So here if you see, I'm saying the author is LLM team, and the description is a AIOS block for chat and multi-model inference. So it is important. These descriptions are important because in the later stages, these descriptions play a vital role in understanding. Let's say we are using an LLM model to automatically discover the right model for any given task, or even say a different a non-LLM approach. These descriptions play an important role for the discovery. So here if you see, I have also included some other metadata, right? Like I'm saying the use case of this particular model is chat completion and also multimodal, right? And the framework I'm using is Llama CPP-Python, and the hardware is GPU, of course. And we also have other parameters like quantization, model path resolution, and who is the provider, right? Things like that. And we can also importantly mention what are its known biases and knowledge limitations as well, so that it can be used in the later stages for further discovery purposes. And we also have the evaluation benchmarks that are available, right, on different, it can be a custom benchmark, it can be any benchmark numbers that we typically want as one of the filter. So that also we can provide it here. So here I have provided for some of the MMLU, the HelaSwag benchmarks. And we also have component init data. So this is, we can have, when we are building this Docker image, so there will be a Python code where we will give the settings and parameters, right? So this component init data is like that. So where here we are mentioning the GGUF file. So since it's a Llama CPP Python, we are using the GGUF to load the model, and we are also providing the clip model because that is used for the multimodal vision capabilities as well. So effectively, this component.json basically serves as a comprehensive passport for the model, right, in the AIOS ecosystem. So that's why it is important. And we also have several other parameters, right? Like if the controlling of the temperature for the LLM model, then we can have some custom parameters as well to clean the sessions. And we have a session timeout, generate parameters again, right? The max new tokens that we want the model to be generated. What is the maximum limit? So these can be checked before the model is started, or even during the dynamic parameter update. So these can be checked as well. That's the purpose of providing all these min and max here itself, right? So you can refer to this JSON again. It has a lot of other important and interesting fields as well. So let's move on to registering this as a, I've already deregistered it. I have made sure so that this works properly. Okay, now let's register this component to the registry, to the AIOS asset registry. Let me run this. Now you can see that there is no error, and it has gotten registered, right? We can also confirm this by running it again, actually. Yeah, you can see that the component with URI model.gemma already exists, right? And remember, this URI that you are seeing is nothing but the component ID. Let me show it again here. Yeah, so we are giving the model type ourselves, and the component ID is Gemma 327B 100 stable version, and that's what it is showing here as well. Right. Okay, now let's move on to allocating a block. So what is allocating a block? Right, now that we have registered the asset, now we can create a running instance of it in the AIOS ecosystem. So a running instance of an asset like this, an LLM model, is what we are calling it as a block. A block is a fundamental unit of execution in AIOS. It's basically a any computational logic that we can keep in AIOS, right? Which will be useful for any inference request or any workload, like the LLM inference kind of things. So when we allocate a block, the AIOS resource allocator finds a suitable cluster and schedules the block for our execution, right? So for more details, you can check these block concepts. Here you have some more interesting information about how the overall functionalities with nice block diagrams as well, right? And it also has a detailed explanation of what each executor, the mapper service that are part of this block also does, right? And also for the APIs and services, you can refer this. You will see some of the services that we have made it available for the block, like checking the autoscaler, the executor, the metrics, and all, right? So to allocate, just how we registered this model as an asset in the AIOS registry ecosystem using a component.json. Here we are also using a allocation.json file. So the main purpose of this allocation.json file is to make sure that when I will share the how the JSON looks now first. So of course we mention everywhere what is the template URI, the parser that we are going to use, so that we can have custom parsers as well. So this allocation.json basically tells what is the block component URI, right? So with this, it connects that it picks the correct component, it picks the correct asset from the registry. Like I said earlier, when we registered the component, we saw that it is model.gemma 3 27b 100 stable version, right? So the same is what is mentioned here. So this is the connection with which the AIOS ecosystem understands and fetches the necessary component metadata, right? And here, if you see, we also provide a few other parameters. Let me explain one by one. So basically, this file tells us what is the block ID that we are giving. So we can have different names. So I am going with Gemma 327b block 2, right? Just for a different demonstration. And we also have the component URI that I told, and we also have init data. So the init data contains the model name. So probably during component registration stage, we can have multiple models as well, right? Maybe we want to use maybe we have created an 8-bit version, 16-bit version, and a BF16 version, things like that. So here we can specify what is the model name that we want to be loaded. We can also mention the clip model name. It is possible maybe in future also there can be different clip models as well. So basically we are giving the model details and the clip model for the clip model name for the multi-model capabilities. And we also have the init settings. So these are settings. So we will have a class where these settings will go and play an important role, right? So for example, there are certain settings like whether we want to use the CUDA or not, right? The GPU or not, and whether we have to enable, if there are multiple GPU, we want to use multiple GPUs, maybe we can enable tensor parallel as well. And maybe if our model is doing, and if our if the Docker image, right, that you have built, if it has capacity to create different quantization types on the fly, right? So that also we can provide. And also some of the initial parameters like the max new tokens and temperature. So these will be created as settings, but some of them we can, as per our definition in the model file, that the Python file that we create, some of them can also be later dynamically updated via some management functions as well, which I will explain. So in this, we also have a policy rule spec, which is what I want to bring some attention to. So let me enlarge this again. Yeah. So what does this policy rule spec contains, right? So this is a very crucial in the AIOS ecosystem. So basically the policy rule spec where we have a lot of freedom, where we have a lot of our customizations. So this is allowed in AIOS ecosystem where these are nothing but a chain of policies. We can have many policies. So let's say I want to have an access checker, like a policing system, right? Where I want to restrict the zones where my model has to, where my model can be loaded. I want to restrict it. I want to make sure that it is running only in certain region or certain cluster, right? I can give those details in this access checker. So the AIOS ecosystem will take care of running this model only in those restricted zones or in the as per the policy that we define. So that is one. Access checker is an important policy, and also we have a cluster allocator, right? So cluster allocator, it understands like if we are sure if there are in the network of clusters, if we want to specify a cluster name, right? That also can be done, and that is, so here I am defining it as a GCP cluster 2. And if we are also interested in mentioning what is the exact node and exact GPU level details, so that also can be done via the resource allocator. And apart from this, we also have the load balancer, which takes care of distributing the load. So here, for the sake of demo, I have configured it to just cache the sessions that we are getting for for a quick response, and also the stability checker. So the stability checker takes care of the health of the block as well, right? To understand whether what is the last update it received, what is the last metric time it has been, what is the last metric check that was done. So those kind of things. I will show one of the health status as well. And we also have an autoscaler, so which takes care of so we can have our own custom autoscaler policies, right? So we here as an example, it could be a token utilization where we can, based on the tokens, the input tokens or the output generated tokens, we can have our own custom logics. And so basically this whole set of policies will make sure that the block that we are allocating is taken care, right? If we have these access checker, all these policies, then it makes sure that the block's health is maintained, the metrics are checked properly, and we need not worry about uh, its continuous uptime and all, right? So basically we are these policies will help in guiding and guiding the AIOS ecosystem to say how the life cycle of the block should be, right? So here we also have other interesting we can, so these are some of the current Docker image that we are using. It has these parameters like the cleanup, the check interval, and all. So that's why we are defining these parameters. And we also can define the minimum instances, maximum instances, right? Like this. And so here I was saying, right, the cluster allocator. So here I'm mentioning that it has to, I'm giving the filter and I'm giving the cluster query as the ID should be equal to the GCP cluster 2, right? And in the resource allocator also, I'm saying it has to use this particular GPU node, and I'm saying it can use two GPUs, this GPU ID 0 and GPU ID 1, right? And we also have the load balancer. For simple reasons, we are keeping a simple load balancer here, and similarly for the autoscaler, right? So this allocation.json now can be used to create the block in the cluster. So let me show you how to do that. So we have this post request where this is the create block is the actual API. So let me run it. You can see, right, it's saying the task has been scheduled in the background, and the return success statement is also true. So so it will take probably some 30 seconds or something, or maybe a bit less than that, to load the model, since it's also a GGUF model. So we'll check the status now, right? So now where are we? Now we have created we are using a base Docker image. With that, we have created a component.json to register the model as an asset in the AIOS registry. Now we are going to do a allocation, and for that allocation, we have just ran this post request. So it has been scheduled, and it will be up and running in few seconds. Now we will see the block status and metrics, right? Okay, now let's check the metrics of the block, right? The status and the metrics. So it is important to understand again that the the ecosystem provides a comprehensive metric system that exposes certain endpoints for health status and resource consumption, which I will show now, so that we can get a complete idea about how the block is operating, right? So basically the metric system is designed in such a way that we can also have some of our custom metrics. We can enable custom metrics to be monitored as well, right? And we have given a starter set of metrics as well, so that those are some of the default metrics, like the CPU related metrics, the RAM related metrics, etc. So for more information, you guys can check this metric system, which we will also cover in a later tutorial, and also regarding how to onboard a custom metrics to our AIOS flow, right? That also will be covered later in the tutorials. So let me just have a quick show here. So this is our metric system. We have different metrics like hardware metrics, block metrics, and we also have something called VDAG, and how to enable metrics for the VDAG related blocks as well. So this is one thing, and we also have custom metrics here, right? So kindly refer these metrics. There are many APIs which we can, once we register it, it will start doing its own monitoring, like 1 minute, 5 minutes, and 15 minutes averages as well. Some of the rolling metrics. So now let's check the status of the block that we have allocated. So this is the old run. Let me run it again. Okay, now you can see, right? It is saying that the last metric is updated just 22 seconds ago. So, and the status is healthy also. So this says that the block is live and running now, right? And let me also show the another metrics. But this is just the health status that we are seeing. And of course, don't forget that we also what is the instance ID is also allocated here. So let me just show it in the KH dashboard. So here you can see I've just opened the KH dashboard. So here let me select the blocks and the pods as well. So you can see here, right? Just 7 minutes ago, this Gemma 327B block has been created, and its corresponding executor file also is created, right? So you can also see the instance ID INO0KCZ. So you can see that ID here, IN0KCZ, right? So this block is up and running now. You can also see some of the logs here. So it is running and ready for our inference request. So now let's move on to the metrics. So whatever metrics I'm going to show here, these are the metrics before we have done any inference. Okay. So and what metrics we have. So some of the core metrics that we have is the CPU usage. There's some of the runtime metrics, right? The real-time CPU utilization percentage, and the memory usage, the current memory consumption, and also the GPU utilization and the RAM consumption. And some of the performance metrics, especially for the LLM things, we need to understand its request latency. We have things like the time for the first token and the total response time, things like that, and the throughput, right? The throughput is nothing but in this case it's a request per second, how many requests our model is able to serve, and also what is the tokens per second that the model is generating, right? So those are some of the throughput metrics, and we also have a queue length to understand the number of pending requests in the queue. And there are some other operational metrics like the request count, the total number of requests that the model has processed so far, and the error rate, right? If there is any errors in the code or some bugs or because of some utilization, so those kind of things. And in general, the health metrics like the uptime, how much, for how long this model has been up, right? So if you think about it, why these metrics are important, so that we can use these metrics later in other, let's say in load balancer, you want to have a custom policy that says that if the error rate is high on certain instance, ignore that instance, right? So we can use such tricks, like such logics to control where we want to do the inference, right? That's the purpose of these metrics. So let me run this metrics request. So here I'm passing the block ID that I've showed you. So Gemma 327V block 2 is the block ID that we have created at the start, right? Okay, sorry, let me. So we have this allocation.json, right? So here if you see, this is the block ID that I have created. So we are basically using that block ID everywhere, right? So here in the block health also, we are using that block ID. And in the metrics also, we are going to use the same block ID. We run it. So now you can see the response, right? So here we are getting what is the uptime. right? So it's basically in seconds. So 610 seconds roughly comes around 10 minutes, which is the time the model would have started. And also the uptime in hours and minutes. And we also mentioning the block ID and what is the current load 15 minutes, load 1 minute, 5 minutes, and the GPU's data that we have discussed. And also some of the LLM metrics here, the LLM active sessions. Of course, we are if a block can have multiple instances. So whatever we are telling here, it is referring to this particular block, this particular instance. The active sessions, CPU utilization, GPU utilization. We have so many LLM metrics that we have added as well. So in the queue length that I was mentioning about, and we also have this time per output token seconds bucket to understand the different kinds, number of buckets, the varieties, the distribution of the time it takes, right? So this is related to the metrics. Okay, now let's move on to do an inference, right? Now what we have done so far is allocated the block in the cluster, and we have checked its metrics, its health status. Now let's try doing an inference. Before doing an inference, I want to mention that here we have I've given some of the utilities in this file, in this folder, inference client. We'll be using those utilities, and also we are making sure that the necessary requirements, Python packages are installed. So let me run this. I think they are imported. And so this is my inference code. I have created it as a function so that we can do an inference later. So basically what it contains is a block ID as a parameter, which is nothing but the Gemma 327B block 2 ID. And we can also pass the session ID if we want to store, right? So that we can maintain the history for that particular session in the LLM. In case of an LLM model, we can maintain its particular history, and also the sequence number. In some cases that can be helpful, and also the message that is required to be, that is passed by the user, and a generation config. Generation config is nothing but what we pass is the temperature, the maximum tokens that we want, right? And in case of multi-model like Gemma, we can also pass an image URL. So these are the arguments, and we also have a server address. Basically, we are doing this inference via gRPC server. So that's why we have this address, gRPC server address here. And so if an image is provided, then the data according to the Gemma model, it has been it should be of this format, right? The messages is a key that we are using in the model, and its content has to be of this type. Like the text should come here. The type of the message should be mentioned like type, which is a text here. So I will pass that particular message, and also the image URL, which I will be passing it within image URL key. And if it is not a multi-model, or if there is no image involved, it will be a plain simple message with the generation config. And we also support multiple modes, but for this tutorial, we are using the chat mode where we can converse with the LLM. And basically here I'm creating the request, right? The gRPC inference packet. So I'm passing the block ID, session ID, and the sequence number and the data. So once that is done, basically we are doing an inference, right? And I'll show by doing an inference as well. So this is the generation config that I'm interested now, right? Here if you see, there is a temperature parameter to understand how much hallucination of the model we can allow. So these are some of the parameters that we are allowing in the model to be used now, right? In case of if it is a non-LLM model or some other compute block, it will have its own set of parameters. Similarly, we have a top P parameter which is set to 0.95, and also the max tokens which is set to 256. So here I'm calling this run inference function that I have defined here. So it's basically we are passing the block ID. The block ID is like I said, it's Gemma 327B block 2. Let me create a different session ID and the sequence number. Since the new session ID, let me keep the session ID sequence number as 1. So the message to the LLM is to analyze the image and generate your own objective scene report. So let me show you an image here, show you the image here. So this is an image where there seems to be some kind of snatching activity, right? A guy is walking near a woman and snatching something, and then there is another person who is an accomplice and they are riding together, and the person as well. So basically we will ask the Gemma model what it understands, right? So here let me also make sure that these functions are available in the notebook, right? Yeah, I think that it has run. So let me run this Gemma model, run this inference now. You can also ask other questions like suggest is there any uh, any snatching like activity. You can also ask that, right? Or perhaps we'll just see how it works with this default one first, then we'll try with the additional prompt. Now the model should be getting a hit. Yeah, I think it has got a hit. And I think it has generated the response. So here's the replay of the model. Here's an objective scene report based on the image. Overall scene it is describing. The image appears to be a sequence of 3 frames captured from a video, showing a street scene with the standing water. So the blur of the image is what I think it is trying to say it as a standing water, but it has captured the fact that there is a 3 set of frames, right? And it is also making up its own things like likely due to rain or flooding, and the key elements and observations is there are several people present. A man in a dark blue shirt and pants is prominently featured, appearing to be assisting someone in the ground. Another person in the green and orange outfit is also visible. A child is lying on the ground. So basically it is describing the image that we have here, right? And the man in blue appears to be helping the child who is lying on the ground. The sequence of images suggests it's a possible incident or assistance being provided, and it is giving its own interpretation, like with caution based on limited information. The scene suggests someone may have fallen or been affected by the flood water, or a bystander is offering help, right? So let me just also try a different session ID here, and I will also ask the model, is there any snatching like activity, just to give it some more context. For our benefit, let us also increase the max tokens here. Then let us see. The sequence number can be same or different, doesn't matter. So I have changed the session ID to 3. Just got a hit. Yeah, it has run now. So now, since I'm giving some guidance to it, right? It is saying that you can see here that it appears there may be a snatching or assault taking place, and it is giving its own reasoning, like there is a sudden fall, right? The woman with the scooter and the man walking with her are upright in the first image. In the subsequent images, the woman is on the ground and the man's position is near the woman. The man in the blue shirt is near the woman as she falls, and his posture could be interpreted as involved in the incident, right? So it is interpreting something based on the guidance that we are giving, right? Probably if you give a better guidance, like how a snatching activity will look, probably it can conclude that there is a snatching activity. So these are some of the interesting things that we can do with such a multimodal capable LLMs, right? And of course, we are printing the latency here just to understand. This is the total response time for this model. So now let's move on to how the metrics are looking after the inference has happened, right? We run this. Again, we are giving the same request here with the block ID. Now, if you see here, there will be some of, so the latency that we saw, right? So the average 1 minute latency, and also the number of active sessions. So since we have started, so there's a periodic update happening to these metrics. So now probably if I hit it again, the number of active sessions will be updated too. So it's an active session, so that is important. And on an average, the session is 1.2. So that's also something we need to understand. So the number of tasks, we have given totally 2 requests. So the total processed tasks are 2. And the end-to-end FPS also it is showing. This is nothing but the FPS related to the first token response. And let me elaborate it a bit here. Sorry. So here, so earlier these metrics were not available, right? The LLM CPU utilization rolling, active session rolling, GPU utilization rolling. So since after the inference has happened, it has started initiating some of the rolling related metrics that I have enabled. So here it is giving the average 15 minutes utility, GPU utility. Then here it is giving the average 15 minutes utility of the CPU. The 1 minute averages are 0 because now it has been more than 3-4 minutes that I have done any inference, right? And also during the inference duration seconds. So this is nothing but we are creating some buckets like a histogram where each response time, each inference duration is created as a separate bucket to understand how many buckets are getting created. And here if you see some of the interesting LLM tokens, right? Especially the input tokens that it has read and the output tokens that it has generated, right? So this is the input tokens per minute, the rolling average. For 5-minute average, it is 292 tokens it has read. We have sent only 2 requests, and the request string also is small, right? So that's why the number of tokens are also 292. And if you see the memory usage also is in bytes, and the output tokens, which is one of the interesting and important metrics in LLM field, right? So we have 343 output tokens generated on an average in the last 5 minutes. And the total prompts that has been created by this model is 584, and the prompts total is 2. So we will have a more deep coverage, but these are some of the interesting and important metrics we have. So here you can also see the queue length, which is of there is no queue pending, right? And again, we also have the metadata of the instance and the node and all. So this is what is how the metrics are changing after we have done an inference. So now let's move on to the interactive chat, where we can where we are using Streamlit to show the streaming capability of the model as well. So I have some of the utilities here that are required to run this. I've already created in the utils folder, which you can find it in GitHub as well. So the block ID I'm mentioning, and the gRPC server address, and also the port number for this particular app, right? So let me run it now. So we should be getting a URL here. Yeah, so this is the Streamlit URL, right? Let me click on that, open it. So here we have the URL. So let me give the same image, probably a different query, right? And here basically we are adding this image to the LLM's context. Let me add it here, and I'm saying analyze the image and generate an incident report, right? A very generic query, and let us see how it behaves. Yeah, you can see, right? It's streaming now. It is not the final response. It's actually streaming the data to us. We are using the model's capability to streaming here, right? So here's an objective incident report based on the provided image sequence. And it has understood the date of the report from the URL that we have shared. And it has the location, it is understanding that it is a paved street and it's a 3-wheeled vehicle and all. So it has given a description about each frame, and it has come to its own conclusion as well. So like this, we can converse with the LLM, right? And it will have its own history in this particular session. So here the session IDs are generated automatically in the backend. And so this is an example to see how you can start conversing with the LLM via chat interface, right? So now let's move on to the cleanup step. So here, let's say we are done with the experiments and we don't want the model to be used further. So what we can do is we can also clean up the block that we have created. So don't forget that we have created a block here, right? Let me log in again. So here we have created that Gemma 327V block, which has been running for last half an hour. So now I don't want the block to be used anymore. So let me deallocate the block, right? So for the deallocation also, via the controller, we are basically sending the block ID here. Everywhere the block ID is crucial, which we are defining it in the allocation.json. So Gemma 327V block 2. And now if you run this, so it is giving a response of action performed and the success status is true. So you guys can see that the case dashboard, it is terminating, the block is terminating, and the corresponding executor is also terminating, right? So this is how you can deallocate a block. And in case we want to deregister the asset itself for some reason, right? Then in that case, we also have this unregister component API, where we can call this API to, with the, of course, the block, the URI that we saw, right? The model.gemma 327v100 stable version. So that needs to be passed so that the AIOS system understands that we are registering this particular this particular block model, right? So it should be terminating now. Yeah, but it has terminated. Now I can also deregister and this and deregister. Yeah, it is saying error is false, and yeah, so basically it has deleted it. So this is the overall end-to-end process for onboarding any model to the AIOS ecosystem. And for more information, like if you want to know how to onboard some other models, like maybe a normal chat model instead of a multi-model, there are several examples we have deployed. You can see here there is Quen, there is Mistral, there is Llama 4. So we have several models like this which we have deployed. And for reference, a similar notebook is what you want means, then you can check it in this link. So here we have this more models, Llama CPP, where we have DeepSeek and Llama. More will be added subsequently as well. Right. Thank you.